topological faces in 3 dimensions as well. And there is also an overcounting here, because in 2D we know that there is a one-to-one correspondence between ground states and also the excitations. So as long as there is a ground state, there will be a corresponding annual that has the same property. And you can use the modular S and T matrices in 2D to describe the Braydian and self-statistics of the 2D annuals. But in 3D, this would cease to be true because there will be more ground states than excitations. So because we have done a twisted gauge theory model, right? Now we can actually consider a simplification that there is no twist, which means the input omega, suppose it is trivial, okay? And suppose that the group is abelian. And one can obtain from the, actually by just simple argument, you can see that ground state degeneracy equals G to the power of Q. G to the power of Q. However, the excitations, number of excitations by just argument in gauge theory will be the size of G to the power of 2. So there is a huge overcounting of the excitations in a 3-dimensional topological phase model. And it would be a much difficult task to really construct the annihilation and creation operators of these excitations in such models. And this would be the next step. Another question to be resolved is that in the 2D case, as I explained, this guy has a well-defined mathematical structure because they are representations of the quantum double of the group G. But in 3D, we don't know what's the mathematical structure of the ground state basis. So this is also need to be figured out. And thank you for your attention. And in fact, actually, if you just keep going on into higher and higher dimensions, you can see that whatever the input data, the co-cycle is, you can even go to n co-cycle. But in the end, it will boil down to a 2 co-cycle, twisted 2 co-cycle. You will always have this it's not doubly twisted anymore. It'll be n twisted probably, and n minus 2 twisted. 2 co-cycle that actually determines characterizes the topological properties of this model. So this is because this is just a gauge theory. This is a gauge theory, and you always have point-like charges, okay? And all the other labels will turn out to be flux labels, and the flux labels indicating the twisting here. So everything will be just twisted except the charge part. So you will always have just the 2 co-cycle that decides what the properties of this these topological phases in high dimensions.
So if the input is abelian gauge,
the input is abelian, then it's much simpler. And input is abelian. You can just reduce that formula. Reduce that the formula I wrote here, which is sum over the number of beta regular conjugate representations.
So do you have a simple answer like for any
I didn't do it in the general case, but we listed examples of certain abelian groups in the paper. Yes, we have answers for certain abelian groups.
So it would be fewer than untwisted?
Yes. It'll be more actually, I think. For V, it'll be more. Because the commutativity between group elements will be obvious.
Any other questions?
So, why do if that depends on two A and B, so why that becomes some group-like representations?
Because you carry two flux labels, you need to integrate over a surface, right, to do this. It implies this kind of two form on the surface, and you integrate over the two form over the surface. And then that's ground state, and if you cut the surface open, you get the excitations along the boundary of the surface. That'll be look like.
If there are no other questions, let's thank Yidun again.